All right, everybody. Welcome to Lab 1. So it's 5 o'clock. Get started here. As usual, if you got questions, raise your hand, turn your camera on. That'd be great. Um, we have a lot to cover tonight, so I'll try to keep up with questions as best I can. If you did some of the pre-work, ask the LLM questions, you might be ahead on some of this, or if you have more experience, but don't be afraid to stop me. We are a quarter of the way through already, I think, almost. So first lab, this is where we're going to get into some, hands-on. And I posted a link to this notebook in chat. I can't remember if I cleared it before I uploaded it. If there's contents in the cells, you can clear it and rerun it. If you don't know what that means, ask your LLM, but happy to help if you get stuck. All right, so there's two homeworks that are due on the 24th. The Jupyter Notebook setup, which a lot of people have turned in, I've been grading as they come, and the data pre-processing for Capstone. Uh, and again, you know my rule, if you turn it in, it'll get counted. So, the 24th is the due date. Um, so we're going to go through introduction to processing data, basic scikit-learn workflow, and some pre-processing techniques. And we're going to do a simple classification problem using scikit-learn. Here's the objectives. Want to make sure you understand the basic scikit-learn workflow. Uh, Common data pre-processing techniques. We'll talk about handling missing values with computer encoding and scaling, why that matters, and apply these techniques to a really super simple problem. Scikit-learn has a bunch of this stuff if you haven't discovered already. As we go through the course, if you get stuck on something, that'd probably be a good place to go and poke around and learn some more, since this is the framework we're using. And as always, right, use your LLM to help you out, right? You don't need a data scientist and a developer to do this kind of stuff. The LLM can really help you. You just got to be willing to have that hacker mentality and figure out what the error messages are, because your LLM is going to write bad code, and figure that out as you go. All right. So we're going to start out with, what is Scikit? Scikit-learn, it's like everything you could ever possibly want for AI and ML rolled into one. And that's almost no joke. It's a simple, consistent framework that has a bunch of examples. It has a lot of documentation. Um, it's not just a training tool. Companies use this all the time for doing experiments and things like that. Before you scale it to cloud scale, you can do it with scikit-learn and prove it out. It's open source, it's free, which is awesome, right? So you don't have to spend any money. You just have to spend the time to start using it. It's efficient implementation, and it handles all kinds of problems. And we're going to talk about all this stuff. Classification, what is a thing, right? Regression, which is predicting an attribute associated with an object, and clustering, which is grouping. We talked about clustering and centroids a little bit, right? And these are all super important, right? Because if you have an anomaly that could be an attacker, you want to cluster it together and figure out what's going on and what's like the other thing, not, kind of where's Waldo. Uh, and then the other question is, why would I use Scikit instead of TensorFlow or PyTorch? Would you learn to drive in a Lamborghini? Probably not, right? Might not have the best experience. This is a good Nissan Sentra, Honda Civic of ML and AI. It's a good place to get started. Okay, so let's talk about data representation. Um, Data typically, it starts out in a bunch of different forms. It can be log files, it can be a CSV file. Um, I got an example here. I'll show you this. This is the data we're going to work with in the example later. It's just a spreadsheet, right? This is the iris data set we're going to work with. And everybody's seen a spreadsheet, but we're going to take the data that exists in this form and we're going to do, pour some machine learning. Uh, rows are samples and columns are features. You've heard me say this before. Um, when you do feature engineering, if you've ever done a formula in a column and created a new value from data that exists in a row, guess what? You've already done feature engineering. Sorry for all the ML snobs out there, but it's not that tough. Data loading, there are a bunch of ways to load data. We're going to do pandas. PD is the kind of de facto definition of it. Read CSV. There's libraries out there that you can import and you can load Excel files. Um, I was just messing around and I created a way to load event files, EVTX files, and pull those in. So you can do almost anything. So don't just think that the only thing you can do is read CSV files, right? We can take almost any input, but for the sake of brevity and explainability, we are using CSVs in this introductory course. Pre-processing, cleaning and transforming the data. Um, if you've ever done data analysis and it drives you crazy because there's rows that have missing values, we're going to talk about how you deal with that using machine learning. Model selection, right? How do you select a model? I've got a cheat sheet that I'll hand out that's actually pretty good that says, which models you should use for what kind of data, right? If you have labeled data, you could probably do something with like the general logistics or linear regression. If you have unlabeled data, you can do analysis with like isolation forest or tree structures and things like that. So we'll talk a little bit about how you get to which model. Training, right? Remember we talked about having a training data set and a test data set, right? How do we fit the model to the training data? How do you make a prediction, right? What happens then as I train the model on the data and then what next? What's that prediction doing? And evaluation, how accurate is it? So this is all standard stuff. You can do this if you abstract this away from scikit-learn. This is a machine learning workflow, right? Data loading, pre-processing, model selection, training, prediction, and evaluation. And it's a continuous loop, right? We go round and round and round. Okay, so missing data. This is the one that drives you kind of crazy, right? The data set we're working with tonight doesn't have any missing data, but you're going to have to deal with missing data sooner or later, right? So we talk about the types of missing data. We have missing completely at random, right? It's missing due to random factors. Everybody has probably seen this if you've ever looked at log files, is you have an entry in the log and it doesn't have all of the requisite metadata associated with it. Don't know why, right? It might have got lost in transit. It might not have been picked up by the agent. It might be in the log on the machine. It never got uploaded to your SIM. So there's lots of different reasons. Could be a technical glitch. Survey responses get lost. And missing completely at random is generally the best case. Then you've got missing at random, which is it's missing in a way you could predict, right, from other observed variables. If something happens, I have missing data. Um, for instance, in a survey, younger people might be less likely to report their income. And missingness has a pattern, but it's explainable by other variables. So you should be able to make some association with other variables that explains the missing data. And then you have missing not at random. and it's missing due to the value itself or unobserved factors, right? Uh, if we're talking about salary, people that make a lot of money don't want to disclose their salary. And this is the most problematic type of missingness as it's related to the missing value itself, right? I just don't want to report that data. So why does missing data matter? Is if you deal with missing data, the easiest way is just say, I'm not going to look at it, but it reduces the sample size. And that that could give you biased results or loss of statistical power, right? When humans start trimming stuff out of data, things like outliers and missing data, stuff like that, you're introducing bias into the machine learning result. And if the missing data isn't random, your model might learn incorrect patterns, right? I don't think that's a valid uh, value, so I'm gonna edit it out of the data, and it ends up being super important to the model, right? So you have to be mindful of that. Use the data that's there. um, there's algorithm limitations, right? Many algorithms can't handle missing values directly, so linear regression neural networks and support vector machines, right? You have to deal with missing values, or it's going to make your algorithm barf. Some algorithms, like I said, decision trees, random forests, they can handle missing data, but they might not do it optimally. So we always try to look for missing data and clean that up as part of preprocessing. All right, so what are some of the common strategies for handling missing data, right? You can delete, right? We just talked about this. You can delete entire rows. You can use available data, right? You can, the pros are that it's simple. The cons are it reduces the sample size. It can introduce bias. We just talked about that. Imputation, this is a good strategy, right? It's you fill the missing data with mean, median, mode, or a constant. You can use other values to predict missing values, kind of like, oh, my model says it should be this, kind of right in the middle. We're going to talk about this some more. Um, the pros are it retains the sample size. The cons are it can introduce bias. And then you've got model-based approaches. You can use algorithms that can handle missing data natively. And you could treat missing data as a separate category. So you could say, okay, so this is a cluster of data. It has something that's missing, and we're going to treat it different. So the impacts are during training, the data, it can lead to biased estimates. During prediction, uh, you need to handle missing data in production, right? Because that's going to happen. Inconsistent handling between training and prediction is poor performance, right? So it all comes down to this, like best practices, understand the data. I don't know about you guys, but when I do data analysis, it's like I just stare at the data and do some basic SQL queries and look at entire rows and groups of rows and try and understand what's going on, right? How many of each value are there that can inform you as far as clustering strategies and things like that, categorization. Um, so make sure you understand that that's why your system expertise is super important, right? Keep notes, right? Document why the data might be missing, even if you're just guessing, right? You got to choose the appropriate methods for dealing with that, right? You can do imputation, right, or more sophisticated methods, but be very careful with how you do this, right? Test different strategies, and then again, consider domain knowledge, and this is all super important. We talked about feature engineering. Sometimes you might have to engineer a feature if you've got missing data to help deal with it, right? So think about all those things. Okay, so encoding. This is an important concept, and it sounds probably more grandiose than it is. Essentially, is most categorical features like names and stuff like that, they need to be encoded because ML algorithms work with numbers. So we looked at this a little bit earlier, right? The iris data, right? This is already encoded, but I want to show this as an example, right? Is the label is the species, but they've already encoded this in the data set. So this is decimal encoding. It's probably not binary encoding, but basically you can take any label and you can encode it into binary. This is simple because we only got 3, but if you have a bunch of them, like hosts and logs and things like that, you can use encoders and it'll do that work for you. But basically this is the concept, right? Is I have a label and I encode it as a number so that my machine learning algorithm understands it, because it doesn't necessarily deal so well with text, right? And if I had a bunch of different labels other than 3, I could have a bunch of different encoding, right? So that's the, sorry for the letdown with encoding, that it's not as grand as you would think it is, right? So there's different kinds of encoders, right? So you can use a label encoder, which converts the text into numerical integers, right? Or you can use one hot encoder, which converts category variables into binary columns, zeros and ones. So here's a little cheat sheet that tells you about the different ones. But I think that label encoding is pretty simple to understand, right? You just do this conversion. And one hot is a little bit more advanced. It's like having a separate yes no checkbox for each category, right? So you still have the different categories, but it gives you a binary representation as to whether it belongs, right? So that, for instance, label encodings be like giving an ID number to students in a class. Sarah gets 1, John gets 2, Marie gets 3. It's compact and efficient, but the algorithm might think John is twice as important as Sarah because 2 is bigger than 1, and Maria is 3 times as important. So it creates what's called a false hierarchy. And the one hot is like having a separate yes no. So is it a DOS? Yes no. Is it a probe? Yes no. No false relationships. But now instead of 1 column, you have 4. So it's a more complex hierarchy. All right. So which method do you use? So look at the comparison table. If you're using a tree-based algorithm like random forest, they'll handle a false ordinal relationship. So label encoding is fine. If you're using a linear algorithm like logistic regression or support vector machine, they'll be confused by those fake relationships. So use one hot. Label encoding for tree-based, one hot for linear algorithms. And that'll make more sense later, but try and remember that. So that's kind of it. We'll talk more about this as we go. The other thing that we're going to talk about is feature scaling. So scaling is important. If you had a relationship where you were looking at network packets and packet size versus some other integer, right? The packet size would overwhelm it, right? So what you want to do is you want to scale your features so they're all related around a median. Remember when we talked about the median, the middle of the bell curve? And what you do from there is you say, how many standard deviations is the value in this cell away from the mean of all the cells? And that keeps it from getting false width. Okay. So I did a little scaling example here. It's a gazillion lines of code, sorry. But it's basically this, right? So this is an example, and we'll come back to this later, but you can see that it's before encoding and after encoding. You can see what the relative weight is here versus what that looks like with respect to encoding, right? So the income looks very large, it has a lot of weight, but if you have it around the median, it looks a little bit different. So we'll come back to this and talk about this at a later slide. So a lot of times feature scaling matters because algorithms are sensitive to scales for just the reason I just talked about, right? Um, and if you don't understand this, take some time and try and grok it, because this might be the most important thing in machine learning. Is if you don't understand scaling, right, it's going to be tough. This is why when you do log analysis, you get funky numbers, right? Is because you're not scaling the features, right? There's time, there's quantities, there's counts and amounts and speeds and feeds and things like that. And they're all different scales. So what you want to do is you want to relate those to say that the mean of all these things we're measuring, I'm within how many standard deviations of the mean. And that way that helps me detect anomalies. So if I have anomalies in several different features, that might indicate, for instance, that we have malware. So here's an example where if you're a hiring manager and you look at resumes, right, and you have a candidate with 5 years of experience that makes $50,000, another has 6 years of experience that makes 100, without scaling, your algorithm might think the salary difference 50,000 is 10,000 times more important than the experience difference 1 year, right? So that's what happens in machine learning. Features the bigger number shout louder, even if they're not more important. So remember that, right? This is a key concept that for machine learning is if you don't scale, you have a hard time doing prediction, you have a hard time doing analysis because your numbers are all over the place. Um, so why do algorithms care about scale? There's two things that we need to talk about, right? Distance-based algorithms, right, measure the distance between data points, right? So like k nearest neighbors is how far is it between me and somebody else that's kind of like me. So if your age was from 20 to 80 and your income was from 20 to 2000, the income again completely dominates the distance calculation. It's like having a ruler where you have to measure inches and miles. You have two complete different scales, right? And then you have the other case is gradient-based algorithms like neural networks use calculus to find the best solution, right? So when features have vastly different scales, the optimization bounces around instead of smoothly finding the answers, right? So again, this super important concept, right? So we talked a little bit about scaling. We're gonna go back to this in a little bit, right? And that's why you get this where if things are scaled, they have an equal voice, and it's not about math; it's about fairness. So again, cybersecurity, you have packet size and response time, and without scaling, you might only care about packet size because it's the biggest number, and you miss timing based attacks. This is historically what adversaries have done with old school things like IDS and some detection algorithms, right? If you're doing atomic detections, you can figure this out, right? And if you're not scaling, you're not really looking at it in perspective, right? So that's kind of it for scaling, right? Uh, all right, we'll talk about this a little bit more. And this is kind of an example, right, of how your income dominates the experience versus age, right? And without scaling, you end up with these um, interesting comparisons that may not necessarily give you what you. All right. So let's talk a little bit about data processing and scaling, and we'll do a little bit deeper dive here. So I guess one of the things is standardization, right? Z-score normalization. This is where you look at each feature and you calculate what the mean, median, mode, and standard deviation is, and you make them all look the same, right? So they're all based around the mean, and the standard deviation is calculated. So the value that is in that particular area is represented by how many standard deviations away from the mean it is. So what's that distance? Is it normal? Is it anomaly? Um, so min max scaling, right? It scales features to a fixed range, 0 or 1. And it's good when you know the approximate upper and lower bounds. And that the problem there is outliers. Robust scaling uses a median and interquartile range, less sensitive to outliers. And unit vector scaling is each sample has a norm, and this is useful for things like text analysis when direction matters more. Um, so, so those are some common scaling techniques. All right, so when is feature scaling critical? Um, this is your scaling cheat sheet, right? This is what I was talking about, right? You'll need this to reference, right? Uh, to decide if you need to scale it or not. The rule is simple. If it's a distance or gradient based algorithm, it needs scaling. If it splits and thresholds, scaling's option, right? So again, tree-based algorithms, neural networks, and that kind of stuff don't usually need to scale. Um, so let's start with always scale group. These will always fail or perform poorly without scale, right? I think I misspoke. I think I said neural networks you don't have to scale, but you do. So neural networks, right? You should scale. So it's, I guess, a way to describe it is if you had a maze and all the slots in the maze were a different size, that would be like a neural network trying to get a result without scaling. Support vector machine, right? That's without scaling, it ignores features with small scales, right? So something that is small is overridden by something that's large, like we talked about. K-means clusters are formed by distance. If you have an unscaled feature, it can dominate the cluster formation, which is why we want to make sure that they're all somewhat normalized, right? K nearest neighbor is literally a distance-based algorithm for a reason. That's the distance between points. We're going to talk about this later. Um, Principal component analysis. Principal components are based on variance, right? High scale features will dominate the principal components. For instance, if we're looking at our malware sample, if we didn't scale, there are some of the values that came from the malware data set that are going to dominate that. So we want to scale so we get a picture of what's going across the entire feature set. And that way we can decide which features are most important, not which ones just have the most scale. So usually don't, right? These work by finding optimal split points, like tree-based algorithms. Decision trees, like the example that we showed in the last class, right? They ask a question. The scale doesn't matter. Is it green or is it red, right? Is it from my friend? Is it from somebody I don't know? So that doesn't change the question. Same thing, random forest. That's just a bunch of decision trees. Same logic applies. Naive Bayes is probability, so it's not raw distances. Even tree algorithms can benefit from scaling those. So if you're doing an ensemble method where you're doing like a combination, you should scale, or when interpretability matters, right? If you want to be able to explain it more easily, you might want to consider. Okay. All right. So without proper scaling, you so scaling mistakes are bad, right? They can cost you big time. they can cost you misdetections, false alarms. This is why it's death by a thousand cuts if you work in a SOC. If you're a tier two analyst, you get a bunch of garbage all the time, right? It's just reality. Scaling just doesn't hurt accuracy. It completely break your model. If you don't scale, you might end up with 60% instead of 95% accuracy. So super important. Um, so when scaling goes wrong, you see predictable symptoms, right? Poor convergence, right? Your network trains for hours and barely improves. So it doesn't find a solution optimally. Uh, I've sort of alluded to this bias feature importance. It thinks the feature with the biggest amount of variance or scale is more important than the other, right? It thinks, for instance, salary is more important than years of experience in the example that we showed earlier. Um, it's You can have suboptimal decision boundaries, right? It means your system might focus on file sizing or behavioral patterns, right? So we'll talk about this a little bit more as we head into the capstone. Uh, this is, for instance, if I have an attacker and they break it up into a bunch of packets that have a small payload, I might miss that, right? Because I'm more focused on the packets size as opposed to the payload, right? So there's definitely pros and cons to this. Um, and unstable results. You can get completely different results if you run it two different ways, and that can be the difference. So benefits of proper scaling is that instead of 1,000 epochs to train your neural network, you can do 100, right? You'll get faster development cycles. Uh, Stable training, your model will converge to the same solution, regardless of random initialization, right? So random seeds, we'll talk about that. That's a hyper parameter that you can tune in some of these algorithms. That gives you reproducible results. So if you change the random seed, I use 42 because that's just what I use a lot of times. But if you change that random seed, you should be able to get the same result. Better feature representation. All features get fair consideration, right? When we talk about feature importance here in a little bit, you'll see why this makes a difference, right? There's, as opposed to size of the feature or the feature scale, it's really how far is this from normal is what we want to look at. So proper scaling, probably 5 to 15% increase, right? So that can be the difference between a science project and a research project. Okay, so best practices, right? We want to be able to figure out what's the proper scaling workflow, understand what you should do in production, learn how to choose the right method, and develop feature-specific scaling strategies, right? These are common and expensive mistakes in pre-processing, right? If you leak data from improper scaling, it has really ruined a lot of ML projects. So the mistake really is fitting your scaler on the entire data set before splitting. It seems innocent, but it's cheating, right? So why is this dangerous? The wrong way is to scale first and then split, right? Because when you split the data, you have some reserve for training, and you don't want to contaminate your training with your test data. And that way you calculate the mean from all the data, including the test set, and then you split it, and now your test set's contaminated because it's been influenced by the impact of the training data set. So again, test and training always need to stay separate. Why is it cheating? Right, your model's seen the information before. It's like, oh, here's the study guide, and it's the actual test. Not that that's ever happened before. So again, split first, then scale. And you calculate the scaling parameters from the training data only, and you apply the same parameters to the test data, and the test data never influences scaling. So that what this means is, right, the difference between a model that appears to work and one that fails catastrophically in production is a lot of times a scaling error. So you can deploy models that seem perfect in testing, but you couldn't detect a new attack because they're overfitted to the test data, right? Through improper scaling. And overfitted means I'm training on something I've seen before, right? Or I'm testing on something I've seen before. So if you have the test data as part of the training data, it's already seen it, and it's going to say, oh yeah, this fits perfectly because I used it as part of the creation of the model, right? So make sure you got to do a couple things, right? Is save your scaler. It's got to be the same scaler that you use during training, right? The new data needs identical pre-processing. Um, when your new data has values outside your original training range, right? You got to think about that and monitor your future distributions in production. If they drift significantly, you might need to retrain your scaler. Okay. Okay. Common pitfalls, right? These three things are probably 80% of the scaling problems you see, right? So if you learn to spot these early, you'll save yourself weeks of debugging, right? Public enemy number one, scaling before the train test split. Um, right? So we talked about this, and sometimes you do it because it feels more organized. Oh, I'm going to clean the data first and split it. But in ML, order matters, right? You gotta split it before you clean it. Okay, so there's things like you spend 6 months developing a fraud detection model and it has 99.8% accuracy, and then you deploy it, the accuracy drops to 65%, and that could simply be caused by you scale before splitting. So you got 6 months of work that are worthless because you got bad data, right? So think about that. Um, so you can't clean data you haven't earned yet. Split it first, then clean. All right. So forgetting to scale new data, right? This is a deployment disaster. Your model works perfectly, but it crashes in production. So you train your model on beautiful scaled data. Everything works great. You deploy it in production and feed it raw and scaled data. Your model thinks normal network traffic is a massive attack because the packet sizes aren't scaled. So this happens, right? You can get flooded with false alarms because somebody forgot to scale, and you got to think about it from a pipeline perspective, right? Your pre-processing isn't done until it's automated for production. So the third pitfall is overscaling, right? And this is a perfectionist trap. You scale everything because scaling's good, right? Yeah, let's scale. So you got to remember what algorithm you're using, right? Tree-based don't need scaling. Scaling doesn't hurt them. The issue is complexity. You're adding steps to your pipeline. So if you don't need to scale based on your algorithm, don't. Uh, but when it matters, if you're doing ensemble, is you mix trees and linear models, you do need to scale. But if you're just doing a pure tree-based algorithm, don't worry about it. And scale when you need to, not because you can. And every pre-processing step can be a potential failure point. All right, so here's a practical example. This is what we were talking about previously, right? Consider a data set with the features age 20 to 80 years, income 20 to 2,000, years of experience, years 0 to 40. Without scaling, the income would dominate the distance calculations because it is orders of magnitude bigger. Paul, you had a question?
Yes, please. It's a quick one. I'm just wondering how easy it is to reverse scale, because when we want to interpret the meaning of the models, we need to reverse scale it back to its natural, its original base or range. So how easy is that to reverse scale everything for interpretability?
Generally, you'll keep the original data in the data frame, or you'll have it as source data. So you'll have uh, a data frame that has the data you bring in. Then you'll have a data frame that has it's scaled. You'll have a test data frame and a train data frame. So you'll have a bunch of different data frames. So you shouldn't need to reverse something back because you'd be reversing back to what you had at the source, if I understand your question.
Well, usually when we've made a prediction and well, because when you scaled it, now it's in from say you use the z distribution, it's from -3 to +3, and then
Hmm.
you make a prediction, and then maybe now you're getting like it's 2.88 something. But how is that related to the salary? Um, in
Well,
well, in the yeah, go on.
yeah, so you'll know what the median is and you'll know what the standard deviation means. And I guess you could calculate it out. That's a good question though. I haven't really thought about reverse scaling. So let's put a pin in that and come back to it. That's an interesting question. I'll go and look around, but I don't know that I understand what you're saying. Is what you're asking, I think, is I have um a feature and that feature has been scaled. And uh, if I make a prediction based on that feature, what is the value as opposed to what is the standard deviation? Is that the question?
Yes, because when we scale it, good and fine, it makes everything as you've explained. It
Yep.
removes all those biases, but then we also lose the physical meaning of those numbers in the
Hmm.
various features. And after we've made a prediction, then it becomes a little bit harder to interpret what exactly it meant when the salary is now -2.77. So
Yep. I
what
know
was
there's
the big,
I,
yeah.
yeah, I know what you're asking. I know there's a way to do it, and it's not on the tip of my tongue. So uh let me get back to that because I could easily go down a rabbit hole here, so I'm going to try and avoid doing that. But it's a good question. Um, all right, so all right, so here's our scaling example, and this is the problem that we're talking about, right? Is you have age and experience and income. And if you look at the raw feature ranges, you can see where the income scale relates to age and experience. And the income dominates the ratios. So income appears to be m- much more important than experience or age. Okay, so um, if you look at these values here, this is a visualization of before and after scaling, right? So this isn't as dramatic as I would like. You should look over here at the right-hand side because I think this is probably uh, more telling than some of these distribution plots. But you can see the feature distributions are of different scales here off to the right, sort of in the before. And then the after feature distributions are the same scale, right? Everything has a mean and a standard deviation. Uh, so they have those scaled values. I'm not sure why this experience bar is up there, but I'd have to go look at the code and figure that out. But you can see where everything is much more normal and there isn't one feature that dominates all the others except for this, one experience bar. And the distribution plots didn't end up being that exciting. They look pretty much the same, but you can see that they shifted ever so slightly, right? Where we have it, instead of having it around years, we have the age scaled and a little bit different distribution. And then the distance components are the, if you look at the difference before they're scaled versus after they're scaled, um, things like income is almost 3,000% larger than age, right? So um, it helps normalize things and it helps you make a better decision, right? So, you know, here's an example. Before scaling, the age range is 59 years. The income range is 173,000, right? Experience range is 40 years. And the experience income is larger than range, right? And after scaling, all the features have similar ranges and all the features contribute equally. And there's not a single feature that dominates, right? So if you talk about that distance calculation, right, because those are sensitive to scaling, right? Before, the income contributes 100% of distance, and age and experience are 0%. And after scaling, it's much more balanced. So if you looked at like a K nearest neighbors for a 3 feature data set, right? You would look at these 3 different people, and you would see that there's a difference in the selection because scaling changed the decision. And that's just based on having things normalized and one feature doesn't dominate. Um, so so here's an example of, I think, what you were talking about in your question, right? The sample data points, right? What's the age, what's the income, what's the experience, and then it's showing you here the same data points after scaling, right? So it shows you, instead of the age is 1.25 less than the median, and the income is 0.98 standard deviations less than median. And this way everything is compared equally, and that helps as we train our models. So the key takeaway is, right, a standard scaler will transform all your features to mean and standard deviations of 1, and the features contribute equally. And you can consider one feature properly, even with large differences in another feature, right? So, in a real world impact, that without scaling, the decision is biased towards income and similarity. With scaling, it's fair consideration of age, income, and experience, right? They're all within some standard deviation, and this is critical for distance-based algorithms. So we just looked at this. I just put that out of the Jupyter notebook. Okay. All right, so advanced considerations, right? Feature scaling is the difference between a model that struggles, right? You can handle categorical features, right? So instead of the feature name, it'll have a number. It's easier for algorithm to deal with. Algorithms don't like names unless you're doing like neural networks and things like that. Time series data that doesn't have, even though time series is my favorite in the past for doing hunting and things like that, um, it's not, it is confusing to machine learning algorithms. And you you need to think about all these things as you're moving along. Okay. All right, so now we're gonna talk about classifying the iris data set. We're gonna load and pre-process it. This is all in the Jupyter notebook, right? We're gonna do feature reduction. So for simplicity, we're only gonna do 2 features, and this is gonna make visualization easier, right? And then we'll filter the data set. We'll split it. We'll choose a model. We're going to use logistic regression because it's a simple problem we're trying to solve, and train it, make predictions, and then evaluate it. And then we'll talk about what accuracy means, and then do some visualization, simple scatter plots. This is all stuff that you'll see this again, put it that way. Come into Jupyter Lab. And I already ran this beforehand, so I'm not going to violate my rule against running demos live, right? So we'll be able to, we're going to go back through the workflow, and we're going to do common pre-processing techniques. These are the same things we set out at the beginning. We'll do simple classification, right? Remember, we're classifying based on a target, right? Is it one kind or another kind? and then we'll apply these and classify the iris data set. And then, as with everything, use LLMs to help with your machine learning workflow. I use this extensively. Uh, all the code started out being generated by LLMs. I have hacked on it some to make it work or do what I want it to do. But in general, I'm doing the same thing that I'm advocating for y'all to do. So we're gonna learn how to figure this out. Okay, so we talked about this again and again, right? Data representation. Data is typically represented in scikit-learn as arrays, right, in NumPy, or pandas data frames, right? Rows are samples, columns are features. So the key step is we're going to load it, we're going to pre-process it, select the model, train it, predict, and evaluate. That's the same workflow that we're going to do over and over again. All right. So first thing is we're going to load the data set from scikit-learn. The data set is in Scikit. All the code's in Scikit, so you shouldn't have to go anywhere but Scikit to get this. So if you have Scikit installed, you're good. We're going to inspect the data, the structures, do some basic data exploration, convert the sklearn dataset format to pandas, right? This is the data right from sklearn, right? Looks like spreadsheet because that's the way the data looks. Um, and uh, and then we're going to explore. So, okay, so the first thing is import your libraries. One thing that I notice is if you use LLMs to write code, they will do the imports kind of in the code block as you're going. I like to put them all at the beginning just because that seems like a better practice. You can leave them wherever you want, but it will make it easier, I think, over time if you have all the imports at the beginning. Random seed, we talked about this, right? Reproducibility. I should be able to go through and run this with my random seed of 42 because that's the answer to life, the universe, and everything. But if I want to change it to 72 or 55 or something like that, I should get the same answer. Okay. So I do all the imports and it comes back because I tell it to that all the libraries are imported successfully. If you do the import and you get an error block here, it's probably because you need to install something. Just do pip install and install it to your Python kernel. The next thing we're going to do is load the iris data set. Okay, so so this is the exact data set that I showed you in the sheet. And what we're going to do is we are going to load the data set. We are going to look at it using some information from our imports up here. Remember where we did these up here? All these things give us these capabilities. So Pandas lets us do info and head and stuff like that. So what I'm doing here is I'm saying a data frame df is
Excuse me, Mr. Smith. I
yeah, go
apologize
ahead.
for. Yeah, can you increase the font size?
Sure. How's that?
Uh, that's better. Thank you.
Yeah, you bet. Thanks for calling out. That's very helpful. I appreciate that. All right. Yeah, that is kind of small, unless you have a 77-inch screen, which I don't. But anyways, all right. So we load the iris data set. We say the iris is load iris. Then we're going to talk about the different shapes of it. So we create a pandas data frame here, and we say iris is load iris, and then the columns are the feature names. Uh, then the data frame species is the target, and the species name are these three here, right? So then we print the dataset info, and we do a head command, which gives us the first few rows. We describe the data set, and then we do some basic statistics, right? So the shape is that we have 150 rows, 4 columns. right? Come back over here and can we check? Yes, we have 150 columns because we have a header. We have the 4 columns, right? The target shape, and then we have the feature names and the target names, right? The targets are the species, right? So when we talk about things in machine learning and data science, we always want to have a target. Is it malware or is it benign? Those are the targets, right? Is it a DDoS attack or is it normal traffic, right? Those are targets, right? Those are also targets are classifications, right? So if I'm classifying something, if I have 3 targets, I can have 3 different classifications. So that relationship is important, right? So then I have some data set info, right? It tells me what the columns are, right? It tells me what if there's any nulls, right? So that's the missing data problem that we talked about. And it tells me what the data type is, right? Remember, if we're going to do encoding, we don't need to do it because they've already done it for us with the species, but the species name is a label that we would have to encode into species as a number, probably to get good results, right? So again, just trying to reinforce this concept. So the first 5 rows, right? So this is the head command, right? It gives me the first 5 rows. And this tells me what that data is. It's just a quick look at it to make sure it makes sense to me. And then some basic statistics, right? So this is the mean, the median, the mode, the standard deviation, right? What percentiles of each one there are and what the maximum value is. It also gives us a class distribution, right? So we have how many samples are there of each one, right? And what is the count associated with it, right? So we know we have 150 rows. We see that each one of the species has 50 examples. And so I would say that's a pretty balanced data set, right? Because everything's nice and even. Um, if we were going to do a classification in an area graph, you'd probably have 3 separate regions, and each one of them would have 50 of these values, but they would, depends on how you cluster them around which particular value. And we're going to talk about that in a little bit. Okay. So handling missing values, we didn't have any in the data set. So, so this does a missing value check on the original data sets, and then it's going to do a demonstration of missing values, right? So, is null.sum lets me know if there's any nulls, right? Drop N8 or remove rows with missing data. Simple imputer with different strategies. This lets you put data in where it's missing, right? We talked about this a little bit. And then we talked a little bit, what's the trade-off between dropping missing data and imputing, right? If you drop, you miss, you reduce the sample size. That may affect the, statistical validity of the result. So dropping is not always good. Okay, so here's the code. I won't go through it line by line, but basically it asks me, are there any nulls, right? What's the sum? And then it prints out the total missing values. And then we're gonna simulate missing data and then randomly introduce some missing values here with this block of code. And then it will show you what it looks like after simulation, right? So the original data set, we know it's clean, right? So for the demonstration purposes, right, we're missing some values, right? We have 10 rows with no sepal length. We have 5 instances where there's no petal width. And then it tells us what the percentage of missing value is. And then we would have to do something with it, right? So our first strategy is like, what are we going to do? We're going to drop the rows, right? And then the second is that we can impute. and then apply it to numerical columns only, because imputation only works for numeric values. It doesn't work for text values, right? So if you have missing text values, you have to come up with a separate strategy. Maybe you just process it and say that's missing. And then we go through the same things we did, right? The difference here is we're using imputer as a, mechanism to fill those empty values, and then we look at the results, right? And this is kind of anticlimactic, but you can see that the first case, we had 15 rows lost and we had 90% of the data. And after we impute it, we have all of the labels, right? And we have 150 rows with 6 features. And we talk about when to use it, right? So if you use each strategy, if you use mean, right, we don't have outliers. Median, we can have a skewed distribution, and the most frequent is categorical or highly skewed numerical, right? So think about that. We'll get into this a little bit. Okay, so we're going to encode categorical features, right? Even though the data set already has encoded them, right? That the species name has encoded, right? Has a numeric value associated with it. We're going to talk about using the label encoder, right? And the label encoding will convert the categories to integers, right? And we talked about why it's good, compact, it works well with tree-based. And the bad news is it implies an ordinal relationship that might not exist, so you might have problems with that with your algorithm. So one hot creates a binary column for each category. Again, no false ordinal relationship, but it can increase dimensionality, right? Because we can have more dimensions associated with it. And the curse of dimensionality is if you're using like tree-based algorithms, they try and evaluate each dimension as part of the tree, and it can cause problems, right? Like convergence to models and things like that. So we're going to talk about label encoder. This is in the sklearn library, and then one hot encoding and the impact on the shape and the algorithm choice, right? Okay, so here's the code. This is fairly straightforward. We're going to use a clean copy of the data. So this is df demo, and we copy that from df, which is our original data frame. We can have size categories based on the sepal length, and we can categorize them based on this, right? So this is kind of feature engineering, right? And then we have a demo of the size category, and we can compare these based on this. So here's where we did this. We created a label, right, size category, and we also have the species name, and we're just looking at sepal length. So the first thing is label encoding, right? Seems like a lot of code, but a lot of it is printing out what we're doing. So label encoding is the original categories were large, medium, and small, and then encoded at 0, 1, and 2. And same thing with species categories, right? The original are these 3, and then they're encoded as 0, 1, and 2. Again, this is kind of already done in the iris data set, but this is a good example of how you can encode this additional text feature, large, medium, and small. Okay, so now the next method is one hot, right? Which is the original, remember our original shape, right? We're up to 9 columns. And then after one hot encoding, we added 4 more columns. So the one hot encoded columns added like a size category encoded, and these are all binary, like ones or zeros. Is it large? Is it medium? Is it small? It doesn't tell you the exact size, but it gives you a binary representation of it belonging to a category. The encoded species, and then a binary notation of whether it's setosa, versicolor, or virginica. So does that all make sense so far? Basically, what we're doing is instead of doing an ordinal encoding, we have a feature for each one of these, and then a 1 or a 0 is associated with whether it belongs to that. So one hot, you get that binary representation, but it can cause issues with dimensionality because you're adding a bunch more columns. And where you're looking at label encoding, again, it might be the implication of some ordinal relationship that might confuse a model. So so you have to be mindful of that as you're going. Okay. All right. Whew. All right. Feature scaling. All right. So we're going to talk about why features on different scales can bias algorithms. So show you a transformation for the algorithms, right? Mathematical, that it'll illustrate the impact of scaling, and it teaches you when scaling is critical versus when it's unnecessary. So again, we talked about this. Distance-based and gradient-based algorithms are highly sensitive to feature scales, so KNN and things like that. Standard scaler is a z-score normalization, right? This is what we talked about earlier with the data has a mean, a 0, and standard deviation of 1. And this is the formula, right? So this gives you the most important thing here is equal feature importance, right? Prevents your features with larger scales from dominating. So we're going to do standard scaler from scalar and preprocessing, talk about fit and transform pattern, and compare the distributions before and after scaling. Again, got some code, creating our demo data. This is we looked at this a little bit earlier, and then we'll dive right into it. Okay, so here's our sample data set, right, that we created. And this is the age and income problem, right? So your data set has different scales, right? Your age can be, 10 times what your experience is. So is that a good relationship? Your income can be, 10 times your age or not. Maybe it can be twice your age. So you have to think about, what's the relationship between all these things, right? As far as across the entire population. So then if you do the statistical summary of that same data, right, there's 10 samples, right? There's count, the mean for each one, the standard deviation for each one, right? The minimum, which quartile it's in, 25, 50, or 75, and then your max, right? So this is the data as it sits. So then we're going to apply the standard scalar formula, which is x minus the mean divided by the standard deviation. And I guess the answer to your earlier question, can you go backwards? I guess if you did the algebra here, you could probably reverse this equation. So that's where I would go. So we look at it before scaling, right? Count, mean, standard deviation mode, right? And then after scaling, right, everything is much more similar, right? So the means and everything. And what this does, all the features now have a mean of 0 and a standard deviation of 1, right? So this tells me, right, that my minimum age is 1.3 or 1.4, let's just call it 1.4 standard deviations below the median, right? And same thing with my income, right? And this tells me which in each one of the quartiles, right, where is that at, right? So if you're in the 50th percentile, your age is this many standard deviations, right? So this really gives you a fair representation of your data as it relates to each other without having to deal with the scale issue, right? Where income would dominate over age and things like that. Okay. So now we're going to do the next thing is a simple binary classification. right? So this is the whole workflow from start to finish. Talks about train test splitting, predict and evaluate machine learning model, and binary classification as a foundation for more complex problems. So we're gonna only do two classes here, right? Setosa and Versicolor. We're gonna maintain a distribution across the train test splits. We're going to use logistic regression because that's a good linear algorithm for classification. And then we're going to look at the accuracy of our predictions. So this uses train test split with the proper parameters to split your data set up. You train a model with a fit of the X train, Y train, right? X is, Y is your category, right? Or your classification. So you always think about Y as your classification. And then your prediction is based on your X values. And then we'll talk about accuracy. Again, more code. So basically what it is that now instead of having, do you remember before we had 4 features and 100 rows? Now we have 100 rows of 2 features, right? So our target shape is 100 rows, and we're only looking at 2 features, right? Sepal length and petal width. And then classes 0 and 1. So that tells us we're only looking at the 2 species. Then we're going to split the data. And this is pretty straightforward, right? If you look at train test split, where we at up here, it uses these values. Here's the test size, 20% for testing. The random state, again, 42. This is a hyperparameter. If you wanted to set random state through this whole thing, you could set it in the up at the top in the imports. And then the stratification, this maintains the class distribution. So that's what this all means, right? Is that we have 80 samples for training and 20 samples for test, 80-20. And now we're going to go through and we're going to train. So what are we doing here? We're going to train the logistic regression model. We select the model here, logistic regression. This is part of scikit-learn, random state, again, 42. Remember, this is a hyperparameter, right? One of many that we're going to talk about, but these hyperparameters are remember, they're the things, they're like the switches for the algorithms. And then the other parameters are figured out as we go. Then we do model fit. So model is logistic regression. Fit is our X train data set and our Y train data set from our split. Okay. So it's going to train the model. And then it's going to make some predictions, right? So it's going to say Y prediction, right? This value is my prediction of category, is my model. Predict is the function of X test, right? So if I look at the X values in the test data set, what is the prediction for Y, which is what species? And then the accuracy is the accuracy score is the Y test values versus the Y prediction values. And then we talk about model accuracy. Then we're going to talk about detailed results. This is going to tell you what the model spits out. And then it's going to give you the prediction results. And then we'll talk about confusion matrix. This tells me how good did I do, right? My confusion matrix is important. And we should calculate this always to see how good our model performs, right? What's our precision? What's our recall? What's our F1 score? We can calculate all of it. Okay, so we trained the model. We made predictions, and it says my model's 95% accurate. So here's the detailed results. The true class is 1, predicted class is 0 is false, but I had 1 false positive. So confusion matrix, right? You can see that it was pretty good. I predicted 10, and I got that 90% accuracy, right? So this is the false negative, and then this is the true prediction. All right, so now what does that all mean? That's great. We got a bunch of numbers. So now we're going to visualize this, right? So we're gonna do a visual understanding how the model performs. We aren't going to calculate it yet. All these values are here in our spreadsheet, or not our spreadsheet, in our notebook, and then we can just do the visualization in this next step. Now, again, I use LLMs to make this stuff, right? I'm not a data scientist. I could probably hack my way through this, but this is where your LLM is your best friend, is when you get into doing this kind of stuff, right? Especially visualization, because there is so much to it. Things like create a mesh so you can have a decision boundary and things like that. And then going on from there. So we're going to have a classification visualization, and have a nice graph for that. And things like you can play with your color scheme. It always seems like it's red and blue. You can change that up if you want. This is related to the decision boundary. How did I get a decision boundary? I went through and I worked with the LM. I debugged the code. I got it running, and I said, hey, I want a decision boundary. Can you create me a function that creates one? And I pasted this in. And then this is all the graphic stuff. And this is kind of what you end up with, right? So all that work, this is what we did, right? So this tells us how accurate our model is. So this is our test data, and these are the labels. Now you can see this line here. This is our decision boundary. This is where our algorithm says that things belong to either versicolor or setosa. So this is my actual true data, right? These are the actual samples, and this is where they lie on the decision boundary. And then I have my test data, which is almost identical to the true data, right? So this tells me what my prediction is. So it predicts these values, and it tells me which category they fall in, right? And then it gives me the prediction accuracy, right? So I had one incorrect prediction, because you can see here in the true data, I was on this boundary line, but I had a versicolor, but it was edging way over on one of the factors, right? Sepal length, or I'm sorry, petal width, right? You see where petal width is right here, and that's right on the decision boundary. So maybe that had an abnormally short sepal length versus petal width ratio, and that's what put it here. But you can see the impact on it. So what I would say is, well, my model's working pretty good, because they got good correct predictions and incorrect predictions. I can see what's going on because I have a good graphic. I can see where the decision boundary is. What can you do to improve your precision and recall, right? You could, if you thought this was a problem, I think 95% is pretty good, then you could change sort of where that decision boundary lies at by manipulating your algorithm a little bit, right? But that would be a hyperparameter tuning you could do, and we'll get into that a little bit more as we go. All right, so what's the insight here, right? The test predictions match the labels, right? And misclassifications, this is a lot of times this is the case, especially with things like linear algorithms, is the closer you get to the decision boundary, the more likely you are to have a misclassification. And this is important to understand, right? Because this is a technique that adversaries use to defeat AI and machine learning, is they figure out how much give do I have in that decision boundary. And we'll talk about this in more in a future lab, but that is super important, is if I'm an adversary and I can figure out where your decision boundary is and how tolerant you are of misclassification, how good is your precision, how good is your recall, I could probably craft an attack that would defeat your algorithm. So that's what people look for when they're trying to subvert machine learning algorithms, right? Is where's that decision boundary? How wide is it? What can I do to get close to it, but not trigger it, or to get something to be misclassified? All right. Okay, so let's talk about scaling and that impact on model performance, right? So this shows us empirically, right? What's feature scaling do to model performance? It's going to show the importance of data preprocessing and illustrate the concept of leakage. So leakage, again, is when information from the test set influences training. Proper pipeline is the fit on the training data and transform both the train and test. And then sensitivity is that some algorithms are more affected by scaling than others, linear versus distance, or distance-based versus, things like neural networks. And convergence, right? Scaled features help us optimize algorithms to converge faster. All right. So again, we got some code. We're going to create a data set. We're going to fit the scaler on training data, and then we'll show the difference between the two. All right, so we're going to compare the performance versus scaled and unscaled, right? So important, right? We split first, and we fit the scaler on the training data. We transform both, and we don't ever let the test data influence their scaling, right? So we'll do it the first time is we do it without scaling. Our accuracy is 100%. Our training time is a millisecond, right? Again, we do it with proper scaling. The accuracy is 100%, and the training time is actually less. So the comparison is there's no comparison change in accuracy, and this is because of the data set. I probably should have chosen a different one, but you can see that the training time is a lot faster. And as we get into like our malware example, you're going to see that if you don't scale some of this stuff, your runtime, it can be 35 minutes. I've had, as I was doing the capstone, I had some things that would run forever and ever, and trying to go through and optimize that. Right. And here's the output of scaling is it's helps with interpretability. The features contribute more equally to decision, and algorithm converges more predictably, so faster. And it's essential for production systems with diverse feature scales, or if you get into larger data sets. And we'll see this. There's a DDoS example where you'll see the impact of scaling, and we'll talk about that in the future. Okay, so then at the end, how do you create a pipeline, right? And this is, how do you take the output of all those different things and make something that's reproducible, right? So this is sort of what it looks like, right? Here's a definition, right? We create the whole ML pipeline, and our inputs are X, Y, our test size, whether we scale or not scale. And again, my favorite, the random state of 42. And again, if I went through and changed this random state to 65, I should be able to run this and still get the same results if my algorithm is good, right? So always, change the random state and check your reproducibility. I should have done it in this demo, but I didn't. But I encourage you to play around with that. All right. So we created a pipeline here, and it handles the test train splitting and scaling and evaluation. And now we're going to test the pipeline. So what this did is it instantiated this pipeline object. So this is living in memory in my notebook, and now I can just run stuff through it. All right. So this is where we test the pipeline with different configurations. And we have our different results. So we test with scaling. Without scaling, you see scale features true, scale features false, and then we'll compare the results. All right. So we run it with scaling, our data set, 100 rows, 2 columns, 2 classes, test size, scaling, our training completes again in milliseconds with 100% accuracy. And if we do it without scaling, same data set shape, same classes, test size. We didn't scale. We trained the model. The model trained faster, but our accuracy was less. All right, so both configurations, they perform well on this particular problem, but your mileage may vary. It depends on what you're putting in the pipeline. And this is super simple, just for the standpoint of going through it one time. And again, we want to consistently pre-process the same way. We want to be able to compare configurations, track results, and have a production-ready code structure, something we can use, and avoid data leakage through a proper workflow. Okay. All right, that was a lot. I don't feel like I even took a breath, and we're at the end of class. So I'm sure there's questions, but that was a lot. I think the best thing is, if you haven't downloaded this notebook or you didn't try to create it yourself, you should go ahead and do that. Either download the notebook and run this and play around with it, or try to generate your prompts yourself using your own LLM, right? So, and these are just graphics of the results. Okay, so now we're to the assignment. So now the question is, could you take the data from the capstone project and do the pre-processing? That's your goal. So I've posted the data's in my GitHub. Pull that data down, use your LLM, and what I would suggest is what I find sometimes works well for data pre-processing is, instead of taking the whole data file you want to feed in, just take a sample. Just take the headers from it and a few rows of data and tag it to your LLM and say, here's the data file I have, and I want to do these things to pre-process it and generate some Python code in a Jupyter notebook to do that, and see what happens, right? So that should take care of it. But think about the principles that we've talked about throughout this lesson, and review those. And again, we want to make sure that we import the data. We need to do label encoding, right? Do we have to do scaling? We need to look for missing values, and do we need to do imputation and things like that? The data set does not have missing values in it. I could put some in if you want, or you could just put some in yourself to see what the impact is, but you should check for them. And then we can kind of go from there. And then that is going to be literally the first part of your capstone project. And that's due with the Jupyter Notebook piece. All right. So we are at time. I will hang around for a couple minutes for quick questions, or you can just put them in Discord. I know we've been kind of going hard here for 90 minutes like usual. So that was a lot. Is anybody's head still attached to their shoulders? Oh, if you got a question?
Yes, I've got a question. Great lab, but I discovered you didn't implement any validation processing. Like, after training, I thought it's best to have training, validation, then test.
Yeah, that's I think that's in there. I might have glossed over it. That's the accuracy is the validation part of it. So and then if you look at the accuracy of the algorithm, but I'll go back and look. I might have just skipped over it, but generally that accuracy, and then the confusion matrix. Did I not have a confusion matrix in this? I didn't. I'm sorry. I thought I did. I thought there was a graphic of the confusion matrix, but no, I don't have it. So I'll add that in. But basically, if you hang on a second. Great question,
You
by the way.
did, yeah.
Yep.
You just had
So
a table of it. Yeah.
yep. Yeah. So I think I had a table for confusion matrix, but somewhere I have this, right? So there's a graphical representation of confusion matrix, and that tells you how well your algorithm's performing, right? Is these are wrong predictions, these are right predictions, so the blue columns, right? So and if you have errors, they'll be in here, and then that affects your overall confusion or your overall accuracy percentage. Does that make sense?
Yes, thank you.
Yeah, you bet. Tutu?
Yeah, so for this project that you just this assignment to capstone, are we is the environment that we are working on, it's strictly Scikit
Yep,
and the LLM? I'm not
yep,
sure what the only notebook I know is the Jupyter notebook.
yep.
There any other no okay.
Well,
So
you can use there's different flavors, like Colab and stuff like that, but they're all basically Jupyter Notebook based.
So for the capstone, you require us to display some type of regression graph from the data that we pulled or data that we um
Just do the basic pre-processing for now, the pre-processing steps that we talked about. So basically what I want you to do is open the file and go through and import it into a data frame. And then, using the techniques that we've talked about here, look for missing values, not a number of values, and that kind of stuff. So basically, if I fed this a CSV file that's formatted for malware, like the one that I'm using for the example, it should process any one of these. So for instance, um, there's a DDoS example that I'll show you later, and I use a sample file to test out the notebook, and then I just pulled a larger example in. So does that make sense?
yes, it makes sense. The examples you've been showing, you showed us some, it looks like coding or some type of programming language, and you also showed us some graphs. Is that the result that the product of the data that you input?
Yes. Yeah.
Okay.
So
Is the
so
graph is the final result?
yep. Yeah. So that's all from the Iris data set in Scikit.
Okay. And so when you use the Iris data set, Scikit will turn the data into some type of regression graphs for you?
You have to ask your
Or
LLM.
LLM? Okay.
Yeah, ask your LLM to write that code for you.
Okay.
So
And
so all the capabilities are in Scikit, though, if that's the question. And your LLM will help you do the Python that gets you a result.
okay, so the LLM will give us a code that we can use to manipulate and prompt the Scikit to produce a regression graphs for us.
Yeah, but that's in we're not all we're doing today is we're just going to open the data file and pre-process and clean
Okay.
the next assignment. But we will get there.
What
Um,
do you suggest to use to do that in the assign? Well, I'm guessing you put that in the instructions in the assignment. The best.
well, you can choose the LLM. Um, so you can either use the one that's in Anaconda, you could use Claude, you could use Gemini, you could use ChatGPT or Grok or whatever your favorite LLM is. But that LLM is what you'll ask to help you write the code.
I noticed that the LLM is sometimes it gives you an error. Um,
Yep.
and even though I'm paying for the Anaconda, but it still gives me some type of error.
Yep, and that's part of what
Oh.
we're trying to learn how to do, is to troubleshoot those errors, right? Because this is part of the new future of being an AI wrangler, is you have to, even without being a data scientist or a Python programmer, you have to figure out how you can leverage LLM to get the results. I think that's one of probably the most important things that I want people to take away from this class is I used to work with a person who just finished up their master's in data science, and he's like, my degree is worth crap now because of LLMs, right?
Yeah, I ended up having to use the Claude sonnet that I have because I couldn't get anything from the AI assistant that's embedded into integrated into Anaconda. I couldn't get anything from it.
I use Claude too. I was kind of frustrated with the Anaconda.
Yeah.
And I think you'll find too, each I think Claude does the best code. Gemini used to, but it's kind of fallen behind. Chat GPT, I'm never sure. Sometimes it's good, sometimes it's not. Haven't used Grok. The Anaconda piece, I was, your mileage may vary with that. Okay. All right, Jose.
Just a quick comment on the ChatGPT. I've been using O4 Mini High, and that's been pretty good, at least for the Lab 1. So I guess it also depends on like which model you use in ChatGPT, but the O4 Mini High was not bad. My question is you said open the Capstone project notebook, retrieve the data file, and follow the steps.
Yep.
Where do I find that? Because I don't see it in Google Classroom. I don't see it in GitHub.
It's actually in the GitHub if you look under the data. Look under main and look under data, and you'll see malwares.csv.
Okay, so dataset underscore malware CSV, that's the
Yep.
data file.
Yep.
And then when you say follow steps to pre-process, those are basically like following the steps that we did in today or reviewed today.
Yep. The basic the machine learning workflow.
Okay. And we should choose like which type of encoding. Basically, because you mentioned like there's different scenarios to do each, and so we should like basically analyze that and choose which type on our own.
Yeah, and again, use the LLM. I could tell you what I did, but I might be doing something different than you did. But you could. What I would do is I would say, I have this data file. I want to pre-process it. What encoding strategies should I use and things like that, and feed the maybe a subset of that data file. I know that it always complains if I put too large like log files up in there. But what I'll do is I'll just open it up in a spreadsheet and take like 100 rows off the top, and then use that to feed to the LLM to help create the model and the code. And then when you run it in your Jupyter notebook, you can run it against the larger bank of code.
Okay. All right.
Yep.
Sounds good. Thanks.
But that's also a strategy you can use, because you don't want to leak sensitive data outside of your company perimeter, but you still want to be able to use LLMs to help you do some of this work, right? So you can feed it the features, right, and just some dummy data associated with it, or a small sample. So, and it will help create the model, and then you can tweak the model once you're working on it inside of in your own Jupyter notebook, right, where it's not exposed to the vagaries of the LLM indexing your data.
Okay.
Right.
Thanks.
Yeah, you bet. Michael?
Yeah, I'm just trying to get an understanding of where we're going with this. So we built a model, and how are we applying cybersecurity? Just because it's a data set on malware?
Right. So what do we want to do? We want to be able to predict from a unlabeled sample of malware data, what's malware and what's not, right? So what we're going to
So the
do
data
is,
set we have is not labeled data.
no, it's labeled.
Okay. So we're gonna use this and then apply it to another data set.
Well, we're going to actually take this data set. We're going to kind of cheat. We're going to take this data set and we're going to run it through and drop that malware column,
Mm-hmm.
and then test on that. It's kind of recursive, but I wanted to keep the complexity low.
Okay, so that's the end goal of this course is just build that model and have it
Right, but
detect
but what I
malware.
want to but what I want to show you though is that you can take any file, any sample, whether it's labeled or unlabeled, and do analysis on it and create a model that you can feed non-sample data to and have it make a prediction. And we'll
Okay,
cover
so
this
that's
more.
the
Yeah, we'll cover this
but
more.
that's
But yeah,
yeah, I
sorry.
just want to see like there's a really like a at least for myself, I'm not really understanding what so we build the model, we're using the AI to help us build the model, um, which makes sense. But what is the end goal? I don't see how this really applies to cyber. Are we supposed to be getting these malware logs or network logs and feeding it
Oh
into
yeah,
different
I can.
LLMs?
I'll show you an example where I take a DDoS attack, log files, and we'll train a model on it. Right. So we're just using malware, but you could do this with anything, right? We're going to do it with network traffic. We're going to do more with Windows logs where we do NLP using TensorFlow on them. So we're just getting
Hmm.
started, right? But basically you can take any data sample and you can find patterns in it. And if you have something that's labeled where you know if it's malware or not, you can train a model that will take an unlabeled file and do detection for you. And
Hmm.
if you don't have a labeled data set, you can do anomaly detection and we'll figure
Hmm.
out, what is good and what is bad, right?
Okay, so by the end of this, we're gonna have X many different cybersecurity models that we can put on our portfolio or something.
Yeah. Yeah.
Okay.
And all these, so we're going to switch, we're going to start using cybersecurity data after this first lab. So
Hmm.
in the subsequent labs, we're going to explore different techniques using actual cybersecurity data.
Okay.
Yeah,
Okay.
we're just using this Iris data set because it's super simple.
All right. That makes sense.
Okay. All right. One more
Thanks.
question. Olufemi.
I was actually trying to get the link to to the capstone project data, so I think I just got it.
Okay. All right. Yeah. If you got questions like that, I just ask them in Discord and Paulina and I will answer them for you. Okay. Last but not least, Paul.
Okay, sorry. Well, maybe I'm looking at the wrong place, but I looked at the data. I didn't quite know exactly what was the target variable, the target feature, and also none of all the columns contained numbers, so none of them was, like text, similar to Iris.
I think the first column has text in it where it's the host. It has like virus total something or other after it. This has been processed, by the way. This is virus total data that has been pre-processed some already. But we'll get into this more as we go. But you're right, there aren't a ton of text data in there. And then the target is the malware column, whether it's malware or benign at the very end.
Mm, Okay, I'll take a look. I may be looking at the wrong file, but yeah.
Yeah,
I'll,
it's in there. But yeah,
okay.
just look for the malware column. That's the target.
All right. Yeah. Thank you.
All right, cool. All right, that's all I got. Again, sorry for running over, but hopefully this is valuable time. And if you got questions, hit me up in Discord or send me an email. All right, thanks everybody.